In this course, you'll learn the basics of writing code in Unity. My only goal is for you to understand how to write your own scripts, to know when to use one technique over another, and be confident enough in doing so that you're able to really start making your own games. The point of this course is to give you the skills to start your project and see it through. In Module 1, you'll learn the basics of writing code in Unity, such as how to manipulate data, how to write scripts and functions, and how to create basic logic. And at the end of the module, you'll learn how to use these techniques in context to create basic gameplay. In Module 2, you'll learn how to use code to solve problems, such as designing your own game systems, connecting the different moving parts of your game together, and how to keep your project easy to change. By the end of Module 2, you'll have a strong understanding of how to solve your own problems using scripts. You'll know how to build the different parts of your game and how to put them together, and importantly, you'll know how to do it all in a way that means you'll be able to finish what you've started. By the end of this course, even if you've never written a script before, you will understand the basics of writing code in Unity. And if you struggle with any of the lessons, if there's something you don't understand, or if you're having trouble applying what you've learned to your own project, you'll find all the help you need in the course's private Discord server, where you'll be able to attend group sessions, discuss your project with other members, and ask me questions directly. Now, let's get started. If you're very new to Unity, while you might be familiar with the basic concepts of the engine, such as scenes, objects, and components, scripts might still be new to you. So what are scripts for, and how should you be using them? Generally speaking, there are three basic ways to use a script in Unity: as a component that gives objects a type of behavior, as a global class that other scripts can access, or as a data template, which is a definition of a type of data or type of class that other scripts will use. Script components are monobehaviors, which means that they can be added to objects in a scene to make them do something. They're monobehaviors because they inherit from the monobehavior class, which is what allows a script to be added to an object in the same way that you'd add a component, like an audio source or a collider, for example. This means that they exist as instances where you can add multiple scripts of the same type and each one holds its own data. Because they're instances, however, when you want to use one, you'll need to have a reference to that instance. When you add a script to an object, certain event messages like update and start will be called on that script so long as it's enabled. These functions, and others like it, are ultimately how you'll connect the behavior that you write in the script to the actual events of your game. You'll learn more about how to trigger logic in your game throughout this course. However, for now, all you need to know is that typically, this is where all logic in Unity starts. For something to actually happen in your game, it needs to happen on an object, in the scene, and be triggered by something that happens, such as an input or a collision, an event that another script calls, or constant triggers such as update. Global classes, or static classes, don't exist on objects. They exist in your project as a whole and can be used by other scripts. When something is static, such as a class, it means that there's only one of that type in your project. This means that, unlike script components, static classes cannot exist as multiple instances. The benefit of that is that when you want to use one, you can do it without needing a reference. You just type out the name of the class to access it. As a result, static classes can be useful when you want to create one-of-a-kind code that everything might need to use. An example of this might be a utility class that contains commonly used functions. Lastly, scripts can be used to define types of data in your game. Custom data types such as structs, plain classes, so not monobehaviors, enums, interfaces, and scriptable objects are all examples of data types that can be created using scripts, and then used throughout your game as a type of data or as a template for something else. You'll learn more on how to use those later on in this course, and in the advanced module. For now though, all you really need to know is that scripts are what make your game happen, and your game happens in the scene. So to get started with scripting in Unity, it makes sense to start by using a script to make an object in your scene do something. When you create a new script in Unity, when you open it, you'll see that some code has been added automatically. So what are you looking at, and what does any of this mean? At the top of your script, you'll see 3 using directives. Using directives allow you to use code from other namespaces, where namespaces are typically an organizational tool to differentiate between different classes that have the same name. In this example, using Visual Studio, the Unity Engine namespace is highlighted, while the other 2 are dimmed. This is because monobehavior exists inside the Unity Engine namespace, so it's being used. The others aren't and can technically be removed. However, when you're getting started, you won't need to worry too much about namespaces. While you may need to add a namespace to use other Unity systems, like the UI or audio mixers, and while it's generally good practice to place your own scripts inside of custom namespaces, especially if you're giving your code to someone else, you can ignore them for now. Next is the class declaration. This defines the accessibility of the script, such as public, followed by optional modifiers, such as if the class is static or abstract, which in the case of scripts that are attached to objects, it can't be. The script's type, which will normally be class, followed by the identifier, which is the name of the script. In most cases, the script's name must be the same as the script's file name, otherwise you'll get an error. After the script's identifier is the script's base class. For scripts that you attach to an object, this will always be monobehavior, or a class that itself inherits from monobehavior. You'll learn how inheritance works later on in this course, but all you need to know for now is that this is what allows a script to be attached to an object as a component, and what allows event functions like update and start to be called on it automatically. You'll see a set of brackets encapsulating the rest of the script. This is the body of the script, and anything placed within these brackets are within the class's scope. So what goes inside the script? Generally speaking, there are 3 different types of code you can place in a class. Variables, such as values and references to data that exist elsewhere. Functions, which are blocks of code that are executed when they're called. And other classes or data structures. More on how you might want to do that later on in the course. Generally, you'd put member variables, which are variables that belong to this class, at the top of your script. This is information that everything in the script is going to use, such as a movement speed float, for example, where a float is a type of number with a decimal point. Other value types include bool, for a true or false value, int, for an integer value, which is a whole number, or vector3, which is a set of 3 values that can be used to describe a position, a rotation, or even a color. It's also possible to reference other classes and objects using variables. These are reference types, and typically point to something that exists elsewhere. You'll find out more about reference types and value types in the lesson on variables. On their own, however, variables don't do anything, they just kind of exist. To actually make something happen, you need to write a function. Functions, sometimes called methods, are blocks of code that are executed line by line when they're called. They are the working, moving parts of your script and are the building blocks of all the logic in your game. So how do you write a function? A function starts with its return type, which is the type of information that it's going to give back. In many cases, this can be void, meaning that it doesn't return any information. Next is the name of the function, which needs to be different from the containing class, and unique, unless you're overloading the function with different sets of parameters. Parameters are the pieces of information that you pass into a function when you call it and are contained within a set of parentheses that follow the function's name. You don't have to accept any data when writing a function, in which case you can leave the parentheses empty. In many cases, you'll need to pass some kind of information to the method when you use it. For example, a move function might accept a vector3 value that represents the movement direction for that frame. That vector can then be scaled by the movement speed value that's kept in the class to create movement. But why keep the 2 values, movement direction and speed, in separate places? Why not put the movement vector with the speed value, or make the speed value a parameter of the function? While you could technically do either of those things, the reason why you might not want to is how the 2 pieces of information are going to be stored. For example, serializing the speed value, or making it public, allows you to control it in the inspector, meaning that you can change how fast this object can move in an appropriate place, on the object in the component that's doing the moving. While the movement vector that's passed into the function is likely going to be controlled by a different script. For example, if the function is made public, meaning that other scripts can call it. A different script, such as an input script that reads the player's input axes and generates a vector3 direction, can then pass that information into the function when it calls it, creating player-controlled movement. But why two scripts? Why not just write one script with input and movement combined? Generally speaking, it's good practice for each script to only do one thing. Since it makes problems easier to find and fix, it limits what each script can do, and it makes it much easier to add, remove, or change how the different parts of your game work. In simple terms, variables are pieces of reusable information in your script. They are numbers, text, or references to other types of data that parts of your script, or even other scripts, will use. For example, it makes sense to give a movement script a speed variable that can easily be changed. This works by declaring a float value, which is a number with a decimal place, giving it a name, and ending it with a semicolon. It's generally standard practice to use camel case in your naming convention, which capitalizes the first letter of each word except for the first. The practice of leaving the first letter as lowercase is used in some languages to differentiate between user-defined parameters and predefined ones. In the inspector, your variable's name will be properly formatted with spaces added for you. The variable can be made public or it can be made private, which is the default if you don't specify its access. Public means that other scripts can read and change the variable. Public also means that the variable is serialized, meaning that it will show and can be modified in the inspector. Typically, you won't always need to make a variable public. So it's generally good practice to keep a variable private, and then if you want it to appear in the inspector, to serialize it instead by using the serialize field attribute. This will show the value in the inspector, allowing you to modify it, but prevents other scripts from accessing it. This is generally a good idea, as it's best to limit how much of a script is publicly accessible. Why? While you'll learn more about best practices later in this course, the short answer is that as you write more and more scripts, you're likely to forget how they're supposed to be used. As a result, it's best to limit how other scripts are able to interact with your class, particularly with its variables. Once a variable exists, the functions in your script will be able to use it in their logic by referencing its name. For example, you can set a variable's value with the equals operator, add to or subtract from it using the plus equals and minus equals operators, or use it in place of a value of that type in calculations in your script. You can also copy it by setting the value of a different variable of the same type to that variable. This is where variables start to behave in different ways depending on their type. Variables will usually fall into one of two categories: values and references. Values are typically numbers, booleans, colors, and similar data types that can be modified in the inspector. They exist where they are declared, meaning that if you set a value to another value, you copy its data. The important point to note here is that if the original value changes, the copy doesn't. Reference variables, on the other hand, are typically links to game objects, assets, and other classes and components. They are essentially pointers that direct towards something elsewhere, meaning that if you copy a reference variable, both variables point to the one same thing. This is the main difference between values and references. When creating a new value at the top of your class, it will already exist using its default value, which for a number, for example, would be 0, or for a boolean, false. While references, on the other hand, can be null, meaning empty, which can cause an error if you try to use them. Instead, references must be set by choosing the object that they point to, either in the inspector or in a script. The value types that you're most likely to use are numerical values, conditional values, and vectors. Numerical values include integers, which are whole numbers, floats, which are floating point precision numbers, typically up to around 6 to 9 digits long, or doubles, which are extremely accurate double precision values around 15 to 17 digits long. Realistically, you'll use integers and floats for most tasks, saving doubles for functions that require increased accuracy, such as audio time calculations. However, decimal place numbers are implicitly treated as doubles, meaning that you'll need to add an F suffix to any decimal number that's intended to be a float. Conditional values include booleans, which can be true or false. You can use them as standalone variables that can be set, or as the result of conditional checks that return a true or false response, such as one number being larger than another. You'll typically use conditions to include or exclude other code from running, such as only performing a task if a checkbox has been set, or doing something over and over until another condition allows it to stop. Vectors, such as vector2 and vector3 values, are sets of floats that are used together to determine a position or a direction. While they're most commonly used to describe where an object is, they can also be used for rotation, scale, and colours. Typically, vector3 values are made up of an x, y, and z float value, specified in that order, while vector2 values, which are more commonly used in 2D, consist of just an x and a y. Both variants exist in integer formats as well, which can be useful for creating rounded grid coordinates. Most basic values are what's known as simple types. Simple types are different types of numbers, letters, and booleans that can be expressed literally, meaning that you can define a value of that type by simply typing it in, without creating it as a variable. An example of this is when using the true or false keywords, typing a number directly, or setting a text string's value. There are different ways to define literal types of the same format, such as numbers for example, and this is why float values commonly require an f suffix to differentiate them from their implicit double literal type. Likewise, single characters are commonly defined by single quotes, while text strings use double quotes. However, not all value types are simple types. Throughout Unity, you'll come across various types of data that acts like a value, such as enums, which are named values that can be used for options and comparisons, and structs. Structs are surprisingly common through Unity, and once you're aware of them, you'll notice them everywhere. In simple terms, they are custom data structures, which allow you to work with built-in functions and pass information around your game. Examples include rays that are used with raycast functions, quaternion rotations, and even values you're probably already familiar with, such as vectors, which are technically structs. Later in this course, you'll learn how to use structs for yourself, and how they differ from plain C# classes which, on the surface, seem identical but work in a different way. For now, all you really need to know is that simple types can usually be expressed literally, by typing their values directly, while structs, even though they are values, typically require setting up with a constructor function if you're going to use new information to set them. This is why if you want to create a new vector3, as opposed to just setting it to the value of one that already exists, you need to use the new keyword and then pass in literal float data into the constructor function. Reference types typically refer to other classes, objects, and components. For example, you can create a reference type of a component, such as an audio source, and then use that audio source to play sounds. However, this only works when the reference is actually set, and trying to use an empty reference will cause an error. As a result, if there's a possibility that the reference could be null, you'll usually want to perform a null check first, which typically involves using an if condition to see if the variable is empty or not, before you try to do anything with it. Other types of variable include collections, which are sets of more than one variable contained within a single reference, such as arrays, which are created using square brackets after the type of value you want to create an array of, and lists, which are classes that require you to pass in the type of data the list will contain in angled brackets. Angled brackets are used when a type needs to be chosen, and you'll see these pop up later in the course when using getComponent and other type generic functions. The general difference between arrays and lists is that arrays aren't designed to be changed, whereas lists are, with functions to add, remove, and reorder them as you need. Arrays are useful for storing fixed data, while lists can be better for storing data that's added or otherwise changes over time. For now though, all you need to know is that a collection contains multiple variables of the same type within a single reference, and they're normally accessed using an element value that starts counting from 0. Meaning that to get a value from an array or a list, all you need to do is pass in the element number that you want when using it, so long as it exists, that is. Collections that haven't been set up in the inspector, or that haven't been initialized with a number of elements, will cause an error when you try to use them, or if you try to access an element that's outside of its range. Initialization refers to giving a variable a starting value, and can often be done by setting the variable as soon as you declare it. This can be useful for giving variables a default value when they're first created, such as when a script is added to an object. For collections, which are object types behind the scenes, this means creating them using the new keyword, at which point you'll be able to specify the collection's length and, optionally, its contents. For variables that don't appear in the inspector, initialization is required to set their starting value. This might be because they aren't serialized or public, or because the variable isn't declared as a member of the class. Member variables exist in your class so that it can be used by everything inside of it, or so that they can be accessed in the inspector or by other scripts. But variables don't always need to be created in this way, and can instead be created as part of a function. This could be useful if the variable you want to create only needs to exist within the context of the function that uses it, and can help to avoid putting lots of variables in the top of your script that simply don't need to be there. It also allows you to manage the lifetime of a variable, as values that are declared inside of a function only exist within that function's scope. Typically, this is for as long as the function runs, which in most cases is inside of one frame, meaning that you can use local variables to keep track of what happens inside of a function, since they're newly created every time it's called, and member variables, the ones you create at the top of your script, to keep track of information that lasts longer than one frame, for the lifetime of the class itself. Functions, also called methods, are the building blocks of logic in your game. In some languages there's a difference between what a function is and what a method is, but in Unity, using C#, they generally refer to the same thing, which is a block of code that takes data in, can return data out, and typically does something in the middle. Put simply, while variables store the data of your game, functions are what will actually make things happen. But how do they work? Just like classes and variables, functions can be private or they can be public, which decides if other scripts will be able to call the function or not. The access modifier is then followed by the function's return type. The return type is the type of information that a function will give back when it's called. For example, a function that counts something might return a number, while a function that checks if something is true might return a boolean. Typically, however, many of your functions won't return anything, in which case they can simply have a return type of void. The return type is followed by the function's name, which is normally capitalized and should be unique. It is possible, however, for two functions to have the same name so long as their parameter signatures are different. Parameters are the pieces of information that will be passed into a function. They are defined by the type of data, followed by their name and separated by commas inside a set of parentheses. Typically, you'll use parameters to give a function the information it needs to work. For example, a movement function might need a movement vector, which can be passed in as a vector3 parameter. This is then scaled by the local speed variable, which is specific to this script and is controlled by you in the inspector when adding it to an object. However, if you don't always want to use the function in this way, it's possible to override the local speed value by creating a second version of the function that takes its own. This is known as overloading, where a function of the same name can be used in different ways depending on the pattern of parameters that it accepts. In this case, to avoid writing the same code out twice, it's possible to simply create one version of the function that does take a speed value and a second version that doesn't, which, when called, simply passes the local speed variable into the other function for you. Parameters can also be used to pass information back when they're called. Examples of this are the ref keyword, which a function might use to keep track of data that happens in between frames, and the out keyword, which is used to give back information in addition to a function's return type. For example, ref is used in the smoothDamp function to keep track of the current velocity of the value it's changing. Normally a function couldn't do this because all of its data exists only in the frame that it's being called in. The ref keyword allows it to read and write to a member variable that exists for the lifetime of the class, in this case allowing it to keep track of a change in velocity over time. While the out keyword turns a parameter from an input to an output. This means that when you call the function, you can assign the out parameter to a variable and read it. The point of this is that it can act as a second return type. For example, raycast functions typically return a boolean value, true or false, depending on if the raycast hits something or not. If it did, the information about the hit is then passed using the out keyword into a raycast hit data type. While it's possible to use these keywords in your own functions, you typically won't need to, especially when writing your first scripts. But understanding that they exist and what they're for can make it a little easier to understand the built-in functions that do use them and when to use them in your own methods. A lot of the time, your function might not need to take in any data at all, in which case you can simply add an empty set of parentheses. The body of the function is defined using brackets, just like a class is. Inside, you'll be able to write statements that create game logic. This might involve changing a value, creating conditional logic, or calling other functions in scripts or on components. Functions can be called by writing their name, followed by the parameters you'd like to pass into the function, if any, followed by a semicolon. You might do this as a standalone statement, or if the function returns data, it's possible to call a function in place of the data type that it will return. Special event functions are called automatically by Unity in a set order. These include functions such as update, start, and other special functions that are triggered when physics collisions happen, for example. You'll learn more about Unity's event order and how you can use it to chain logic together later in this course. When a function is called, its logic will be processed line by line until it reaches the end of the function's scope, or if the function is manually returned using the return keyword. Return is an optional method of stopping the function early and can be used with conditional checks to exit out of a function if continuing might cause an error, such as before trying to use a reference that's null, for example. It's also how you'll return data from a function, where a method that has a particular return type must return a value of that type in all its possible code paths. While variables store data, functions are used to create logic. But how does that work? How can you create the logic inside of a function? While you'll typically execute behavior inside of a function by calling another function, logic can be created by assigning, comparing, and evaluating variables. And typically this is done by using operators. In very simple terms, an operator is a symbol that allows you to assign, compare, or otherwise manipulate data to create logic. For example, you've probably already used the assignment operator, which uses an equal symbol, and sets the value of the left-hand operand to the value of the right. Like the assignment operator, most operators are simple, self-explanatory, and easy to use. However, there are many that are less intuitive, but that can be extremely useful once you know that they exist. One of the most common operators you're likely to use is the member access operator, or dot operator. This provides access to the members, meaning the publicly available variables and methods, of the left-hand operand. If you've written any code in Unity before, then chances are you've already used this operator, and you'll typically use it to dig down into subdirectories of a reference to reach a particular variable or method. The index access operator, which uses square brackets, allows you to reference an element of a collection, where the number that you pass into the operator is the element that you want to use. This allows you to access one element in an array or a list, or, more often, allows you to use every item in a collection by passing in a dynamic reference, such as in a for loop, for example. You'll learn more about loops in the lesson on iterators. However, for now, in this example, I is simply an integer that's added to and reused to access each item in the collection in turn. It's possible to use a member access operator conditionally by using the null conditional access operator. This takes the form of a question mark that precedes the access operator and checks to see if the left-hand operand is null before trying to execute the right. It basically works as a short circuit where, if the operand may be null, a check can be performed before going any further. You'll commonly see this used when invoking delegates, as it's a simpler way to check that the delegate is set to something before it's called. It's basically a shorthand null check, which is easier to type and simpler to read. But if that's true, why is it only commonly used with delegates? Why not all kinds of nullable references? The null conditional operator doesn't work correctly with object references, meaning game objects and components. This is a quirk of Unity where, in order to check if a game object reference is actually null, the underlying C++ engine needs to be checked. The null conditional operator bypasses this check, meaning that it doesn't work, causing an error if the reference is null. Generally speaking, all this means is that you shouldn't use the null conditional operator to check for object or object-related references. Instead, use the equality or inequality operators, which have a custom implementation in Unity, meaning that they work how you'd expect them to. The equality operator can be used to check if one operand matches another, while the inequality operator can be used to check if it doesn't. Typically, you might use these operators to check if a reference is or is not null, either by only executing a code block if the reference exists, or by returning out of a function early if it doesn't. The equality operator can also be used to check if two things are the same. For example, comparing two variables, such as numbers, allows you to check if something is a specific value or not, while comparing two references will let you check if two things are the same or not. This works on an instance basis, where the operands can be of the same type, but will only evaluate to true if they actually refer to the same thing. This can be useful when creating a singleton, for example, where you typically check if a reference matches the specific script it's being checked from, or allowing an object to exclude itself when looping through a list of objects of the same type. The less than, greater than, less than or equals, and greater than or equals operators work pretty much exactly as you'd expect them to, and allow you to perform numerical checks that either include or exclude the target number. For example, the less than operator is commonly used when looping through an array, where the last element inside of its range would normally be one less than the length value of the array itself, meaning that in this case using less than instead of less than or equals avoids an out of range exception. Arithmetic operators can be used to manipulate numbers. For example, the addition and subtraction operators can be used to add or subtract numbers together, while the addition assignment and subtraction assignment operators can be used to add or subtract from an existing value without overwriting it. Essentially, this is the same as assigning a value to itself, plus or minus an additional amount. Typically, arithmetic operators are very straightforward. However, there are a couple of use cases where they can be used with non-numerical data. For example, string concatenation works by adding strings and values together using the addition operator, while the addition assignment and subtraction assignment operators are commonly used to add or remove functions from a delegate. The increment and decrement operators increase or decrease a value by 1. Typically you'd use these for loops, where incrementing a counter, for example, would allow you to loop through all of the elements in an array. Multiplication can be used to multiply numbers and can also be used to rotate a vector, where multiplying a vector by a quaternion, which is a rotation value, will rotate it by that amount. The division operator can be used to divide one number by another. This generally works how you'd expect it to, except that it's worth paying attention to the implicit type of the left-hand operand. For example, if you assign a double value to the result of a divided integer, you'll only get an integer back. Adding a d suffix fixes this problem, as the whole number is treated as a double when it's divided. The remainder operator, or modulo, returns the remainder of the left-hand operand after division by the right. For example, 5 modulo 4 returns 1, while 13 modulo 5 returns 3. This happens because 5 goes into 13 twice, leaving 3 behind. This can be useful for all kinds of mathematical calculations, especially when calculating tempo or similar measurements of progress inside of a fixed unit. While there are only a limited number of arithmetic operators, it's worth mentioning that Unity includes a large selection of mathematical functions via the mathf class. While there's too much in this class to cover in the scope of this lesson, we'll be looking at some of the more common mathematical functions in the working with numbers lesson later in this course. Boolean operators return a true or false value and are typically used in if statements to determine if a block of code should be executed or not. The logical negation operator is used to return the opposite state of a value. For example, when using a Boolean value in an if condition, it's possible to check if the value is true by simply passing in the variable. If the Boolean is true, the code block executes. Likewise, the logical negation operator can be used to check if something is the opposite of true, meaning false. This is functionally the same as using the equality operator to see if a value is true or not. It's just simpler to write, and should generally be used when you want the opposite of what you expect it to be. It's also possible to use the logical negation operator to check if a reference is null. This works because it's possible to check if a reference exists by passing it into an if condition directly. The logical negation operator can be used to check if a reference does not exist by checking for the opposite of a reference. Logical operators can be used to evaluate multiple conditions together and typically come in two variations: logical operators and conditional logical operators. Standard logical operators such as the AND, OR, and exclusive OR are denoted with a single symbol. For example, AND will evaluate true if both operands are true, OR will return true if one of the operands are true, and exclusive OR will return true if one operand is true while the other is false. Logical operators always evaluate both operands, even when doing so would be unnecessary, while conditional operators, which are denoted with double ampersands and pipe symbols, for conditional AND and conditional OR, will only evaluate the right-hand operand if the left-hand operand is true, or, in the case of the conditional logical OR, false. This means that generally speaking there are very few cases where you'd use the standard logical AND, since if the first operand isn't true, there's really no reason to check the second. However, while rare, there may still be times when you'd want to do this. For example, it might be that the operands are functions that ultimately return true or false, but still execute other code, in which case you may want both operands to still be executed, even if the condition ends up returning false. Generally, many of the available operators can be used in place of each other. The only difference is that some operators are simpler to write and take up less space, which can be extremely useful in a large script. One operator that's extremely good at this is the ternary conditional operator. The ternary operator is basically shorthand for assigning one of two values depending on a condition. It works by assigning a condition to the variable you want to set, followed by a question mark, followed by two possible values that can be assigned to the variable, separated by a colon. If the condition is true, the first value is assigned. If it's not, the second is instead. This is functionally the same as checking the condition in an if statement and assigning one of two values based on the result, except that it takes up much less space, and when you're used to using it, can be much easier to read. When you're first getting started in Unity, you're less likely to use the bitwise and shift operators, but they can be helpful in a couple of very specific scenarios. When dealing with layer masks, for example, which use the binary representation of integer values to flag specific layers, it's possible to use the left shift operator to identify a specific layer in code without using a layer mask variable. This works by shifting the bits left by a certain number, which, when performed on the number 1, moves the active flagged bit to the layer that you want, while the bitwise complement operator can be used to flip all of the bits, which in a layer mask allows you to exclude a particular layer instead. Conditional statements, such as if statements and switch statements, can be used to include or exclude code from being executed. You'll typically find yourself using some kind of conditional statement quite often, as they allow you to run different logic depending on what's happening in the game. At a basic level, an if statement can be used to check if something is true, and if it is, run the contents of the code block in response. This works by passing in a Boolean condition, such as a function or a comparison using an operator, after the if keyword. Then, if the condition is true, the statement executes, and the contents of the brackets are run. For example, a function that reduces the player's health might check to see if it's below 0 every time the function is called, and if it is, destroy the object. Or if a raycast function returns true and something was hit, you can use the if statement's code block to do something with the result. You can pass just about anything into an if statement, so long as it can be evaluated to a true or false value. If statements are executed if their condition is true, but it's possible to check for a false condition by using the logical negation operator, or an equality operator to check for the value that you want. However, it's also possible to execute different statements depending on the condition's result. For example, the else statement allows you to run one block if something is true, or the other block if it isn't. If-else statements can be easy to use and are typically very easy to follow. However, if you're only using an if-else statement to set a variable to one of two values, it can be easier to use the ternary operator instead, which does the same thing just on a single line. Else-if statements work in a similar way to if-else statements, except that they introduce additional checks. This also allows them to be used repeatedly to create multiple different conditions where, if one condition is not true but the next one is, that block is executed instead. It's even possible to end a chain of else-if conditions with an else condition, allowing you to create an if all else fails option that will be executed if nothing else turns out to be true. However, using multiple if statements to evaluate a number of different conditions can start to become messy. Switch statements allow you to evaluate one condition and then run one of a number of different statements in response. This works by declaring what you will measure and then creating case statements that execute based on the result of the measurement. Each case may match one possible outcome of the measurement, executing if one of them's true. Functionally, this works in the same way as an else-if statement, except that it can be easier to follow. For example, an else-if works through each statement until one of them is true, while a switch statement executes the one case that matches the measured condition. Technically, this isn't any different to how an else-if works, since if multiple switch statements are true, the first statement will be executed anyway, like an else-if. The difference is that a switch statement is more suited to picking one of many possible options based on the result of a single measurement. And if none of the above are true, a default case can be added that is executed if all else fails. A switch case must break out of the enclosing statement when it's executed, and typically you'll use the break keyword to do this. Alternatively, it's possible to return out of a switch statement, either to end the function at that point or to return data back. You'll probably use if statements a lot in your code, which is fine. They're extremely common, and writing logic without conditional statements would be extremely difficult, if not impossible to do. But if you find yourself writing multiple if statements with many different conditions, or nesting them inside of each other several layers deep, it's worth considering if there's an easier way to do what you're doing. For example, functions that are dependent on multiple checks, where one failure would cause the entire function to be stopped, can be gated with a single if statements that return out of the function if the condition is met. You'll learn more about the different ways to manage different sets of behavior later in this course. However, for now, while you will need if statements and switch statements, and you should use them because they can be extremely useful, it's worth keeping in mind that if your if statement feels complicated, then there may be an easier way to do what it is you're doing with it. Iteration statements, also known as loops, are a way of doing the same thing more than once based on a variable condition. They're an extremely common part of writing code in Unity, and you'll typically use them whenever you need to do something over and over again, which is a lot. For example, if you want to check all of the elements in a list of objects, you'd do that with a loop. If you wanted to do something a set number of times, you'd do that with a loop too. Or, if you wanted to keep doing something over and over until something else happens, you guessed it, loop. While they are very common, writing a loop can be a little tricky at first. But once you know the structure of a basic loop, you'll find that they can be extremely helpful in a lot of different tasks. So what goes into a loop? A for loop, which is typically the most common type of loop you're likely to use, is defined using three main elements: the initializer, the condition, and the iterator. These are used to execute an iteration, which is the block of code that's run each time the iterator loops over. The initializer is only executed once, before the loop starts, and it's typically used to create an iterator counter that can keep track of the loop's iterations. More often than not, this will be an integer, starting at 0, and called something short and simple, such as I. This value serves two purposes. It's the counter that measures when the loop is actually done, and it acts as a dynamic element in each iteration, allowing you to identify a changing value, such as exactly which object in a list it is that you're referring to. The condition is a check that is run every time the iterator loops over, and basically it's an if statement for the iterator's code block. The loop will keep running so long as this condition is true, meaning that, since for loops commonly execute entirely inside of the frame they're started in, this condition has the power to freeze Unity if it's used the wrong way. As a result, the condition that allows the loop to execute must be changeable from inside the loop's execution. This usually involves using the counter value that was created in the loop's initializer and comparing it to a value that represents the scope of the loop. For example, if you want to loop through every element in an array, you might create a condition that evaluates to true so long as I is less than the array's length. Or, when iterating through a list, the list's count value. This works because I is the changing value, or at least it will be once you add the final part of the loop, the iterator. The iterator is a statement that's executed after each loop, and generally you'll use this to increment the loop's counter. This is important because without it, the iterator would loop infinitely, freezing Unity. Inside the iteration, you'll be able to use I as a dynamic variable. For example, if you want to do something 10 times, the condition would be where the counter I is less than 10. Each time the iterator loops around, the block will be executed and the counter will be increased by 1. Debugging the iteration block reveals this, however your experience of it will be that it happens all at once. This is because for loops typically execute inside of the frame that they're called in, meaning that they loop round as many times as they need to before moving on. For example, a loop that iterates 10 times works in functionally the same way as calling a method 10 times in a row. That is, unless you stop the loop early. If a loop has already done what it's supposed to do, it's possible to stop it early with the break keyword. This exits the loop at its current point and passes control back to the calling function, which will carry on as if the loop finished. Likewise, if you need to skip over a particular iteration, it's possible to do that with the continue keyword, which stops the current iteration and moves on to the next. In context, you might use the continue and break keywords when searching through an array of references. For example, let's say that you've got a list of game objects and you want to find the first one with a particular tag, such as the player tag. In this example, we're also going to assume that some of the references in the list may be null and must not be checked. It's possible to do this by continuing if a reference is empty and breaking when the object that you want is found. Realistically, this might be all that this particular function does, in which case instead of using break, which only breaks out of the enclosing loop, you could directly return the result that you want, stopping the loop and the function entirely. In this example, when the return type of the function is a game object, if nothing is found, because the loop completed without finding the player, you'll still need to return something, as all code paths must return a value of the function's type. In which case, because nothing was found, you can simply return null. For loops can be useful for doing something a set number of times. However, because the iterative element involves checking a number of actual identifiable objects, it's possible to perform a for each loop, which is designed specifically to iterate through the elements of a collection. This works by removing the counter and identifying the type of object that you're checking instead. You'll assign a named reference to the type, which, in the iteration, will represent each of the different objects that you check. For loops and for each loops typically evaluate a known number of iterations, operating within specific limits. For example, a for loop that does something 10 times will stop after 10 iterations. However, it's also possible to execute a loop where the total number of iterations is unknown, using a while loop. A while loop works in a similar way to a for loop, except that it doesn't have a counter. Instead, it has a single condition which, when true, will cause the loop to iterate over and over. This works in a similar way to an if condition, where if the condition is true, the block is executed. However, while an if condition is only executed once when it's called, a while loop will repeat over and over for as long as the condition is true, which can be a problem. Remember that, under normal circumstances, a loop is executed inside of the frame in which it's called, which means that unless a while loop is able to change its own condition, a while loop that's called inside of a regular function may loop infinitely, completely freezing your game. This is because the rest of the frame is never allowed to finish, and nothing else can happen that may change the while loop's condition. That is, unless you put it in a coroutine. Coroutines have the ability to yield their execution until a later time, usually until the next frame. This means that even though the while loop is still technically running, it's possible for something else to happen that would cause its condition to change, breaking out of the loop. While conditions only execute if their condition is true, meaning that when a while loop is first evaluated, if its condition is false, it's never run and it's skipped over entirely. A do loop works in basically the same way as a while loop, except that it'll execute its code block at least once first, after which it's repeated while the condition is true. Timing, specifically the order in which things happen, is surprisingly important in Unity. This is because most unexpected errors, as in something that was working but now isn't, or something that usually works but sometimes doesn't, are almost always to do with changes in timing. This happens because while there are some asynchronous operations, generally speaking, Unity operates on a single thread, meaning that two things cannot happen at the same time. One thing will always be processed first, while something else must be processed second. But what comes first? The logical order of events in your game is determined by three main factors: Unity's event execution order, instance-based ordering, and function-based chains of execution. Event execution order refers to the built-in methods that are triggered by Unity on monobehavior objects such as start, update, fixed update, and collision functions. These are triggered in a specific order, determined by Unity's event function execution order, and together they make up the lifecycle of a frame. For example, you probably already know that update is called every frame, while late update is always called after update. Yield, which is the process of suspending and interrupting a coroutine, happens just after update does. This refers to actually yielding a coroutine. The code contained within a coroutine before it's yielded will run whenever it's called, just like any other function would. It's only when the function is suspended that it's processed in the yield event message. Fixed update, which is the physics system update call, will always take place before update, and may be called once, more than once, or not at all. This is because fixed update calls are triggered at a different rate to frame updates, at 50 frames per second by default, while frame rate is generally variable. But while fixed update does run at a different rate, it's not asynchronous. Instead, fixed time is compared to delta time, which is the duration of the last frame, and fixed update is called enough times to keep up. This all happens within fixed update, meaning that even if multiple calls are required, they all happen here, before update, after which fixed update won't be called again until the next frame. Collision events such as on-trigger enter, exit and stay, and on-collision enter, exit and stay, happen next and are called when a valid collision of that type has occurred. For this to work, at least one of the colliders involved must also have a rigid body attached, which is the component that allows an object to move under physics, and when using on-trigger, one of the colliders must be a trigger collider. Finally, after the physics functions have ended, input events are called before the frame's update loops begin. Lifecycle events such as awake, onEnable and start are called when a script is first loaded, any time it's enabled, and the first time it's enabled. Awake and start are commonly used as two-stage first-time initialization methods, and you typically want to use awake to set up an object relative to itself, while start is commonly used to set up an object with other objects. An example of this would be a class that gets a reference to one of its own components in awake, so that when another script tries to use that reference in start, it's definitely already been set up, avoiding an error. OnEnable is typically used with onDisable to activate or deactivate parts of the script or object when it's turned on and off, such as when subscribing to events, for example. They're also called when the object is created and when it's destroyed, at which point onDestroy is also called at the end of an object's life and after all other event functions. It can help to think of this order as something that Unity dictates, not something that happens independently on an object. So Unity calls all of the starts for all of the scripts in the scene, and then calls all of the updates, and then calls all of the late updates, and so on, where each event function is called in every script on every object before moving on to the next. The exception is awake and onEnable, which are called in order but as a pair on a per script basis. This means that awake and then onEnable are called in one script, and then they are both called in a different script, and so on for all of the objects in your scene. While the event execution order is set, this order, the order in which scripts will have their event functions called, is not. It's random. So how can you know which script instances will have their events called first? The short answer is that you can't. The longer answer is that while you can control script-specific execution order, it's generally better not to, at least most of the time. The order in which scripts are executed can't be predicted, and while it's usually the same in a single project or on a single machine, loading the project elsewhere or building the game typically results in a different order. This is why so many seemingly unexplained errors can appear when you build the game for the first time, since a change in order may mean that a previously undetected timing issue may now cause a problem. It's possible to force certain scripts to have their functions prioritized over other classes by adding them to the script execution order, which allows you to weight a class so that it's executed before or after others. However, ideally, this should only be used as a last resort for very important, time-sensitive scripts. It also only works at a class level, meaning that a particular type of script will have its functions called before others do, but the instances of that script will still be random. It can't even be guaranteed that all of the object's scripts will be called together, which is why staging logic into event functions that are always separate can be useful for avoiding timing issues. However, this won't always be possible, and for closely linked logic, it can be better to chain dependent logic together to create an order of events that's linked to function execution. Function execution refers to the flow of logic that happens when a function is called. If it helps, you can think of this as Unity's train of thought. For example, when a function is called, its statements are executed line by line from top to bottom in order. If one of those statements calls a function, then the flow of execution moves to that method immediately, finishing it before returning to its own function to carry on. This could happen multiple times over, where functions are essentially chained together directly. This can be useful for controlling the flow of logic without breaking it, which can be a good way to avoid errors that might be otherwise introduced in the gap between ending one function and starting another. But why is this important? A real-life example of this causing a problem was in an early version of my hobby project, which involved moving objects around on a grid. The player could hold an object and put it down, but only if it was in a valid position. The objects would manage their own status, updating whether or not their position allowed them to be put down, which at the time made sense. But because the function that caused the object to change its position and the function that checked if it was correct were separate, it was possible for the object to report that it could be put down before the player moved it. As you now know, this is because the order of update calls on both objects could not be guaranteed, and without changing one of the script's execution order, there's no way to know which would be called first. This meant that the object could be placed in an incorrect position if the player happened to move it from a correct one and tried to put it down within the same frame. The solution to this is to chain the logic together so that it's all triggered from a single call. In this case, player input. The object no longer uses update to check if it's in a valid position. Instead, it holds a public function that returns a boolean and that's called when trying to put the object down. Generally, this is how a lot of functions in your game are likely to work. They'll be triggered by a limited number of events, such as player input, the passing of time, or something that an enemy does that causes a chain of logic to start. And understanding this can help you to avoid timing-related problems. As a general rule of thumb, when writing a behaviour, consider what trigger will cause it to happen and how the timing of that trigger could affect it. Then either directly link the behaviour to the trigger that will cause it, such as an input that executes a chain of events, or stage it in a way that means passive functions that are dependent on other events but that are not directly linked, such as, say, camera movement that responds to player movement, takes place in a different event function, such as late update, for example. When you start to build your game's logic, one of the first problems you're likely to run into is how to manage the connections between your scripts. It's generally a good idea to try to keep code that does different things in separate scripts. The point of this is so that you can easily add, remove, or reuse them elsewhere in your game. But this creates a new problem in that now your scripts will have to talk to each other. So how do you do that? The easiest way to connect two scripts together is to do it manually. This works by creating a reference variable to the type of class that you want to connect to. So this might be a component on an object, or a script that you've written yourself, and then make it serializable, either with the serialize field attribute or by making it public. This will force the reference to appear in the inspector, at which point you'll be able to drag an object of that type to the field, or use the circle select button to choose a compatible object from the scene or the project to connect it. You can then use the script's publicly available functions and data via the reference you've created. This is generally the easiest and most efficient way to connect two scripts together in Unity. However, it's not always the most convenient, and it isn't always possible to connect your scripts in this way. For example, auto-implemented properties, such as variables with a private set, won't appear in the inspector, while objects that are created while the game is running can't be set up manually by you. In which case, you'll need to create automatic connections by using getComponent. GetComponent is basically a search function that can be run on an object to return a component or a script of a particular type. It can be used to automatically create references between scripts, or to check if a particular object has a particular type of component on it. For example, an enemy script might want to get a reference to a player's health script to damage it. This works by passing the type of component that you want to get into the getComponent function in angled brackets. Angled brackets are used when a generic type needs to be specified. In this case, getComponent needs to know what type of component it is that you're looking for and will return a reference to it if it's found. If nothing's found, the function will return null, which is why it's usually a good idea to check if something was found at all before trying to do something with it. This implementation of getComponent can be a little messy unless you're basically certain the component will be there. As a result, if there's a chance that it won't be, it can be easier to use try_getComponent instead, which does the same thing but returns a true or false boolean depending on if the component was found. Which is useful as it allows you to call the getComponent function and then only do something with the result if there actually is one. By default, getComponent returns the first component of the specified type on the object you call it on. It's possible to get all of the components of a certain type by using getComponents, which places multiple matching results in an array. While to get a component that's on a child or parent object, getComponent in children or getComponent in parent will search those objects instead, starting with the root object and moving outwards. GetComponent is basically a local search operation, which, while it's very useful, can be inefficient if you use it in the wrong way. Generally speaking, it's fine to use getComponent to set up your scripts, and it's fine to use it to create new connections while your game is running. However, you're likely to run into performance issues if you use it too frequently. By frequently, I mean calling getComponent in update over and over again, every frame when you don't really need to. Most of the time, you'll want to use getComponent once when creating a new connection, and then cache that reference for use later on. This avoids having to repeatedly search an object for a component that you've already found. GetComponent is a game object function, meaning that you can call it on a component's object directly by typing getComponent without a preceding member, or on a different object if you have a reference to it. But if the object you want to check is outside of your script's local hierarchy, how can you get a reference to it? There are typically two ways to create a connection between two anonymous objects. They can connect directly, such as touching, colliding, or otherwise physically interacting in some way, or they can be connected remotely. Direct connections generally involve physical interactions, such as when objects collide or are detected using a physics function, such as a raycast. This is a common way to interact with objects, as pretty much every physics interaction also allows you to get a reference to the object you're interacting with via its collider. And while there are other ways to create connections between objects, using the physics system to detect when objects directly interact with each other can often be the simplest way to do it. That is, unless the two objects don't interact. Remote connections refer to the relationships between objects that have no direct interaction, such as the player and a menu, or an enemy and the score. They never touch, they don't collide, but they affect each other. So how can you connect objects and scripts together remotely if they never interact? A basic method of creating a remote connection is with a find operation. Find operations are typically scene-wide searches that can be used to find an object with a particular name or tag, and that can be useful for creating connections between objects and very important scripts that aren't otherwise connected. However, because they're search operations that take place in the entire scene, they're generally very wasteful. As a result, if you're going to use a find operation, it's best to only use them sparingly, at the start of a scene, and to avoid using them at all while your game is running. However, it's understandable why you might want or need to use a find function. After all, global connections between objects and important systems in your game can be some of the most difficult types of connection to get right. Luckily, however, there are other ways to do it, such as by creating global variables, for example. A global variable, in this sense, is simply a variable that everything has easy access to. It might be the player's health, or a game timer, or the score, or some other important metric that multiple systems have an interest in. The simplest way to create a global variable is to make it static. The difference between something that's static and that isn't is that a static variable is shared by all of its instances. For example, it's possible to create multiple versions of the same script that exist on different objects. Each of the instances hold their own data, which can be different between each one. Marking a variable in that script as static means that it's not different, and that it is instead shared by all instances of that class. Why is that useful? Static variables and static functions can be accessed directly from their class type, meaning that you can use them even if you don't have a reference to them. This is generally how singletons work, where an instance of a script, such as a game manager, holds a static reference to an object of its own type. Everything can access it, and through it, its public references and data, without needing to be connected to it, touch it, or find it in the scene. However, statics can cause problems if you use them in the wrong way. Because they're so convenient, it can be tempting to overuse them. A general rule of thumb is that statics work well when there will absolutely, definitely only ever be one of that thing in your game. For example, an audio manager is a good use case for statics, as it allows any object to play a sound effect, and there will definitely only ever be one audio manager. Using static variables for your player, however, might seem like a good idea at first, but then if you ever add a second player, you'll find that all of your scripts are hard-coded to work with the player, not a player, meaning that you'll have to completely change how your game is structured in order to add a second. You'll learn more about the different options for passing data around your game later in this course, in the advanced module. For now, however, when implementing a method for connecting scripts together, a good measure of how effective it will be long-term is how difficult it would be to change it later on, as a project that's easy to change is generally easy to work with. When you're building your game, and especially when you're learning how to use Unity, you're going to get things wrong. You'll make mistakes and there will be errors, but that's a good thing, as the only way to fix problems in your game is by knowing what's broken. In fact, you may find yourself deliberately breaking parts of your game in order to change how it works, allowing the errors that are generated to show you which parts of your game need updating in response. You'll find log messages, warnings, and, importantly, errors in the console window. When you're first getting started, there are two types of error that you'll want to look out for here: compilation errors and runtime errors. Compilation errors refer to mistakes made in scripts. They mean that your project can't compile and, as a result, can't be run. Double-clicking the error will take you to the line of code that's causing the problem, where you can fix it, save the script, and then return to Unity where the error will be cleared automatically. Runtime errors refer to a problem that's caused when your game actually runs. One of the most common errors you're likely to run into is a null reference error, meaning that you tried to do something with a reference that was empty at the time. Selecting the error will show you which object in the hierarchy caused it, while double-clicking will take you to the offending line. Runtime errors can sometimes be tricky to pin down, as it means there's nothing technically wrong with your code, at least in that it's able to compile, but something's happening that's causing a problem. Sometimes you'll know exactly what you've done, while sometimes it will be less obvious. To work it out, start with the error. You'll be able to see the line of code that caused it, and the trail of functions that led to it happening. However, if you're not sure what your script is doing, and when, it's possible to send your own messages to the console to work out where the problem is. The debug log function will log a message to the console and can contain a text string, a variable's name, or a mixture of data types. This can be helpful for reporting back data at critical points in a function to see if it's what you expect it to be, which can help to find out which part of your code is going wrong and why. While log messages can be useful, they can also be harmful for performance. Firstly, because they write data to an actual file, and secondly, because log messages create garbage, which is an unused memory allocation that has to be cleared up. Generally, this isn't a problem when you're building your game, but it can be an issue if you leave lots of active log messages in your final product. There are a few different ways to avoid this. For example, you could exclude debug messages, either by commenting them out or by using platform-dependent compilation, which is simply an if condition for the compiler that will, in this case, only include code if you're in the editor. Alternatively, you can disable the player log when building your project, which prevents the costly process of writing to a file, but won't stop debug log from being called. Or you can disable the logger entirely. A good way to do this is to set the log-enabled property to the value of the isDebugBuild property. That way you'll still get log messages in the editor and in development builds, but not in your finished game. However, removing the log or disabling the logger, while it will improve performance, won't prevent garbage from being created when strings are concatenated, meaning when they're added together. Preventing log messages in this way can also reportedly cause issues with crash reports that may rely on them being active. As a result, one of the most effective methods for handling your own debugging messages is to create a custom log message function. Then, make the function conditional on the Unity editor symbol being present. This means that the function and any call to it will only be compiled for the editor and not in your finished game. Log messages can be useful for working out what's going on in your game, but sometimes you'll want to see what's happening behind the scenes when your game is running, especially if something isn't technically breaking but just isn't working in the way you expect it to. For example, you can switch the inspector to debug mode, which will reveal hidden data, including non-serialized variables. While in your scene, it's possible to see if positional calculations are working as you expect them to by drawing lines and rays to work out if your normally invisible physics checks are working as intended. These will be visible in the scene view by default, but if you want to see them in the game view as well, you'll need to enable gizmos. Lastly, while debugging can sometimes be frustrating, if things aren't going to plan, a general rule of thumb is to isolate the different parts of whatever it is that isn't working. A lot of the time, this is all debugging really is, and simply removing each individual part of a function to see what it does and if it works in isolation will get you most of the way there to solving your problem.